A linear relationship is one of the simplest relationships between two sets of data. Creating a linear model can help you make predictions without obtaining the data for each value. The basic equation for the linear simple model is y equals mx plus b, but when trying to find the model of best fit, error is also added into the equation. This brings the equation to a more formal version, y equals beta naught plus beta 1x plus epsilon, though additional dependent variables and corresponding beta values can be added for more complex linear models. The residual plot is a graph of the distance each point is from the generated line. Not to be mistaken with error, the plot does not influence the line of best fit, but instead is used to determine how far off each individual point is from the model. One thing that the residual plot can indicate is whether there is a nonlinear model that would better represent the data. Should the residual plot show a trend, it is likely that another model would be more effective. In this case, the points are randomly distributed about the line, so it follows that a linear model is the reasonable choice.
When creating a linear probabilistic model, there will be some error for each point. The error, denoted epsilon, is normally distributed around each y value of the graph. The error makes it possible for many different linear models to represent the same data. The best model is the one with the least amount of error, which is usually calculated using least squares regression. The value that is used to determine how well the model fits the data is the r-squared value, also known as the coefficient of determination. If the r-squared value is close to 1, that means the model represents the data well, and you can make predictions using your model with more confidence. If the coefficient of determination is less than 0.4, it is likely that the model is not the most accurate and there may be a better model to represent the data than a linear model. Knowing the variation/error also allows the probability of a certain outcome to be determined. As the error creates a normal distribution of possibilities centered about the model, the same process can be used with a standalone normal curve to determine the probability of a value occurring given the standard deviation and mean value, both of which are intrinsic to the model. This allows for the calculation of probabilities such as that a value increases or decreases as expected, or the chance that a y value occurs at a given x.
This image is an example of when using a linear probabilistic model would be useful in real life. The graph comes from some of my research that I do for UCF, and it displays the stress over strain in an experiment. I could use linear modeling to find the elastic strain by calculating the equation for the graph before it reaches its first max. This would allow us to estimate the deformation of the material depending on the amount of pressure it experienced. There are countless other examples of real-life applications. These may include the rate of manufacturing versus the amount of time before a tool or part breaks, or the amount of heat generated based on the load a component experiences, such as brake pads. Because of its versatility, linear probabilistic models are one of the most widely used tools in statistics.